Today we're going to talk about density and solubility. So pretty basic concepts, but we just want to make sure we have an understanding how to calculate it, how to measure it, things like that. Okay, so density is defined as mass per unit volume. So when we look at our equation, we're gonna have D, M, and V. So D is gonna stand for density, M is gonna stand for mass, and V is gonna be volume. Okay, so when we calculate this, it's dividing mass by the volume. Okay, there's gonna be three different, you can't see it, sorry, units of measure for density. There we go. So if it's a solid, it's going to be grams per centimeters cubed. A liquid will be grams per milliliter, or a gas will be grams per milliliter. Okay, so density itself is a comparison of how much matter there is in a certain amount of space. So if you were to look at these two boxes, let's say the dots in the box represented people in a square. Okay, so which square is more dense? Okay, it's going to be the one on the right. But what about now? Now they have the same number of people, right? But what's the difference? The difference is in the amount of space, okay? So in this instance, the one on the left would actually be more dense because it has more people in a given amount of space. So here is going to be our equation, okay? So D equals M over V. Density equals mass over volume. Guys, this is why our units are grams per centimeters cubed or grams per milliliter, because it's the unit of measure of mass over the unit of measure for volume, okay? So let's just make sure we're good with mass and volume. So mass we find, remember mass is the amount of matter in an object. To find mass, you're going to use the triple beam balance, and we're going to measure this in grams, okay? This is a picture of a triple beam balance, and yeah, should be good with that one. Now volume. So we've talked about volume before, and volume of a liquid, we can use a graduated cylinder, which we see here, okay? But if it's not a liquid, if it's a regular shaped solid, so like it's cube or something like that, we can easily do length times width times height. Now I expect this equation to be prior knowledge, so if you're not quite sure about it, please write it down, okay? So length times width times height. Now please understand that when we do that, that is going to give us a unit of measure of centimeters cubed. But that makes sense because centimeter times centimeter times centimeter gives you centimeters cubed. Okay. If it's just a liquid, we'll use a graduated cylinder. Okay, and we want to make sure we understand the water displacement. And I think we've talked about this before, but just to review it again, if I have an irregular shaped solid, so like a rock, and I needed to get the volume of that, I can't do length times width times height. Okay, I can't just drop it in a graduated cylinder. Okay, I'm going to do this thing called water displacement, and that's when you fill a graduated cylinder up with a certain amount of water, put the object inside, and see how much the water goes up. And you're going to, however much the water rises would be your volume. Okay. So let's do a couple of practice problems. Okay, so the first one says Frank has a paperclip. It has a mass of, sorry, I'm making sure I'm going to write on this, a mass of 9 grams and a volume of 3 centimeters cubed. What is its density? Now guys, sometime more than likely, I'm not going to be so blatant about this is your mass, this is your volume. Okay, obviously we're just starting to practice this, so I am. Please understand though, if it's measured in grams, you know it is your mass. If it's measured in centimeters cubed or milliliters, you know it is your mass. Your volume, excuse me. You don't need me to tell you that. Okay, our equation is going to be D equals M over V. Now, real quick, guys, before we go any further, I'm dividing, so I'm gonna round my answer in the end to sig figs, okay? And my least number of sig figs is 1. So, oh gosh, go back. Is 1. So we don't want to forget that, okay? So we want to make sure in the end we're rounding to 1 sig fig. All right, so let's look at our math. So we do mass over volume. Okay, and it's going to be grams over centimeters cubed. I do highly recommend holding onto your units for this, just for the fact it helps you make sure you write down your units in the end, okay? So how many times can 3 go into 9? 3 times, okay? And do not forget your unit of measure, okay? None of these little guys cancel out, so that in and of itself is my unit. So it's going to be grams per centimeters cubed. Now I'm already down to 1 sig fig, so I'm done. Okay, again, super simplified, but once we get the equation, it should easily apply to anything else. All right, so I want you to try the next one. Frank also has an eraser. It is a mass of 3 grams and a volume of 1 centimeters cubed. What is its density? So just in case, I know you could probably do this in your head, but just in case, for good measure, let's write it out. D equals M over V. Our mass, we said, was 3 grams, and our volume is 1 centimeter cubed. Remember, we want to go down to 1 sig fig in the end, okay? So our answer is going to be 3, and you have to have a unit of measure. So grams per centimeter cubed, okay? And that would be my answer. All right, so let's look at the next one. The next one says, Jake has a rock. The rock has a mass of 6 and a volume of 3. What is the density of the rock? Can you solve this? Again, we're starting off with basic math. You probably don't even need a calculator. We want to make sure we're going down to 1 sig fig, and my answer is going to be 2 grams per centimeter cubed. So please, 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 please catch that I'm getting this unit from right here, okay? All right, our next one, Jill has a gel pen. The gel pen has a mass of 8 grams and a volume of 2 centimeters cubed. What is the density of the pen? And now again, guys, these are very basic math equations or calculations, but please understand, if we've got the basic on how you do it, when we supplement other maybe more challenging amounts, it should be fine because it's the same idea, okay? All right, so I got 4 grams per centimeters cubed. All right, we're not gonna do this. Okay, let's keep going. All right, so when we talk about density, oftentimes we talk about liquid layers, okay? So when we talk about liquid layers, sorry, I'm trying to move my face out the way. If you pour liquid layers together and they have a different density, they won't mix, okay? They will actually form the layers. More than likely, you know that oil and water don't mix. Well, why? Because they have different densities, okay? So a really, really, really good example. So the liquid with the highest density is actually going to sink to the bottom, and the liquid with the lowest density is going to float to the top. Okay, and then they're going to layer, if you have more than just 2 liquids, they'll layer out from there. But again, the higher densities are going to be towards the bottom, and they'll progressively get less and less and less dense until you get to the very top. Okay, so if we were to look at this picture, which layer has the lowest density? So the least dense layer will be the top layer. Technically, I guess you could say it would be the air, depending on how deep you were going with this. If we were, imagine we have the liquids that have the following densities, 10, 6, 3, and 5. Which number would go with which layer? Okay, so if we were gonna number these out, the greatest density is gonna go on the bottom, so 10 grams per centimeters cubed. And then a little less dense, so 6 grams per centimeters cubed, and then 5. This dark spot right here, that's just a shadow, okay? And then 3 grams per centimeters cubed, okay? So very, very basic idea, but again, a lot of times it's been a while since we've gone over it. So if we were to look at this again, which liquid has the highest density, that would be your greatest dense, let's see, syrup. And the liquid that has the lowest density, what would that be? Now remember, I'm saying liquid, so don't tell me air because I specifically said liquid, okay? So oil, and then what about middle density? Water, very good. All right, we're not gonna try this on wrong. Normally I do. Oh gosh, that's all over the place. Okay, so just remember the formula for density is D equals M over V. You're simply plugging in your numbers. You do want to make sure we're continuing to hold the sig figs. And yeah, that's it. So pretty easy, pretty straightforward. Sometimes I will give you the sides and you have to do length times width times height of like a cube. Sometimes it may be the format of an irregular shaped object and it tells you that it's dropped in the liquid and it's raised so much. Okay. So those are kind of the different ways you'll see it. Now we need to talk about solubility. Now we mentioned, so both of these things that main ideas we're talking about today are things that we talked about when we mentioned physical changes and physical properties. Okay, so solubility. Solubility again is whether or not a substance will dissolve. Okay, so let's talk about two components of a solution. Okay, so the solute is the substance that's being dissolved. So in this case, it's a powder. Okay, the solvent is the dissolving agent. Okay, which is the water. Now, water is known as a universal solvent because it dissolves so much stuff. So, examples, sugar water. In sugar water, sugar is going to be your solute and water is going to be the solvent, right? What about salt water? Okay, in salt water, what's your solute? And then what's your solvent? Okay, so your solute would be your salt and the solvent would be the water. Okay, very good. All right, so the amount of solute that will dissolve, solubility is the amount of solute that will dissolve in a given amount of solvent, okay? So it's either going to be soluble, meaning it will dissolve, or insoluble, meaning it won't, okay? And this varies with the solvent. So guys, if you think about Sharpies, so a good example of this is Sharpies and water, okay? Water does not dissolve Sharpie, right? It stays. But rubbing alcohol does. So I totally thought I had a picture there. So solubility varies, okay, with the solvent. Think about sugar water and sand and water, right? Sand and water, that's insoluble. They do not mix together. Sugar water, that's soluble. They do dissolve. All right, so let's look at factors that affect solubility. Temperature is a big one, and pressure. This unit, we're going to focus more on temperature. And then as we progress in our semester or a year, we will start focusing a little bit more on pressure. Solubility is the amount of a solute that will dissolve in a given amount of solvent at a given temperature and pressure. All right, so different factors that affect the rate of dissolution. Okay, so stirring. Okay, stirring will help things dissolve more rapidly. Temperature. Particle size or surface area. So a big block of sugar is not going to dissolve as rapidly as small granules of sugar, right? Okay. All right, so let's talk about some terms. Okay, and we're almost done besides just some examples. So a saturated solution contains the maximum amount of solute that will dissolve in a given solvent at a specific temperature. So if you add more, it's not going to dissolve. This is the maximum amount that will dissolve. Notice, this depends on temperature, okay? This depends on temperature. If you've ever gone to a restaurant and ordered sweet tea and got unsweet tea and you tried to add sugar to it, you see that sometimes it doesn't quite dissolve like you think it should because now it's a cold liquid and you're trying to dissolve the sugar. But if you were to heat it up, it dissolves much better, okay? That temperature aspect. Okay, an unsaturated solution contains less than the maximum amount, okay? Meaning you can still add more to it and it will still dissolve. So saturated, maximum amounts dissolved. Unsaturated, less than the maximum's dissolved. And supersaturated contains more solute than more solute than is present in a saturated solution at a specific temperature. So supersaturated is more than the maximum amount. And this is like your rock candy. Have you ever made rock candy? So you put so much sugar in it and you have to keep heating it up and heating it up and heating it up and adding more and more and more. And it can't hold all that sugar, so it starts to fall out or crystallize, right? Okay, from the substance, from the solution, which then forms your rock candy. Okay, sodium acetate crystals rapidly form when a seed crystal is added to a supersaturated solution of sodium acetate. It's the same idea with sugar. Okay, so here's an example. Here's the image. Okay, so we added, do you see the seed crystals added? And just watch it spread. Okay. Now, and again, I said spread. That's probably a poor choice of words. But the sodium acetate is dissolved in this liquid. Okay. And because it's supersaturated, the moment this seed crystal is added, all the solute kind of will attach to it. And then you see it coming out of the solution. So just another way of looking at it. Okay, you have your unsaturated solution, okay, which more solute can still be dissolved. Okay, as we're increasing concentration of our solute, you then get saturated where no more solute will dissolve. Meaning if we continue to add more, it's just gonna float to the bottom, okay? It's not gonna actually dissolve. And then you have your supersaturated solution, which becomes unstable and crystals form. Again, rock candy. Okay, here is what our solubility graphs or charts look like. Okay, a lot of times students completely forget when they see this because they see so many lines and it stresses them out. Do not let this stress you out. It is simply a graph that you are reading. It just plots and illustrates several different substances. Okay, so do not let this bother you. Do not let this stress you out. Okay, this is not a super challenging concept. Okay. All right, so if we look here, the lines that have the arrows attached, okay, these are all substances that solubility, remember, the ability to dissolve, okay, the specific amount increases with the temperature increasing. So notice, so for KNO3, at 0 degrees Celsius, it had what, let's say, that's probably 25, like 15 grams was the saturated amount. So the maximum amount that could be dissolved. Okay, but if you look here, these bottom two arrows are showing you two substances that the solubility actually decreases as we increase temperature. Okay, and that's totally something you're going to see. You're not reading it wrong. Okay, it's just one of the characteristics of these substances. Okay, as the temperature increases, less and less will actually dissolve. Okay, so let's look at this line. Okay, this is showing oxygen gas, solubility and temperature. Okay, when we look at solubility curves, okay, no matter which direction the curve is going or how great the slope is or not, please understand anything on the line, any points on the line itself are considered saturated. Okay, that's the maximum amount that's soluble. Okay, if you were given a point below the line, okay, that would mean that more substance could actually be dissolved, right? Which would mean it's unsaturated. And if you were given something above the line, that means more substance is dissolved, which means that it would be supersaturated. Okay, so solubility, with oxygen gas usually decreases with the increase of temperature. And again, we pointed that out in the last one. So just make sure you understand that it's okay. Okay, it's okay. All right, so let's look at some practice problems. All right, so the first one says, what is the maximum amount of NH4Cl that is soluble at 50 degrees Celsius? Okay, so don't get freaked out. I know there's a lot of lines. All right, but let's look for NH4Cl. Okay, so this is the line I'm looking at. And it wants the maximum amount, so it wants the saturated amount of this substance that is soluble at 50 degrees. So let's find 50 degrees. My temperature's at the bottom, 50 degrees. We're going to go up until we hit the line that we're looking at. And it's asking me for the maximum amount. So let's look for a measurement. So this is going to be 50 and 50 grams. Okay, so 50 grams. All right, so let's look at the next one. The next one says, at what temperature would 30 grams of KCl be saturated? So again, saturation is on the line itself. So this is asking me for a temperature. It's given me a gram. by grams. Now, oftentimes, it may say at what temperature would 30 grams of KCl dissolved in 100 grams of H2O. Okay, don't let that mess you up. Look over here at the labeling, okay, of your y-axis. Okay, all of these substances are going to be in 100 grams of water. Okay, so we're not worried about that 100 grams of water. We're worried about the 30 grams of KCl. So let's go over to 30. All right, so here's 30 grams. Make sure you're looking at the right spot. We want to be on our gram side, not our temperature side. And we are looking for KCl. Okay, so here's KCl. So let me try to trace it so that I'm looking at the right line. Okay, so 30 grams would actually be right here. And it's asking me for a temperature, so we're going to drop down. And we know we are looking at 10 degrees Celsius. Okay, the next question says, which two substances have the same solubility, meaning it can dissolve the same amount at 28 degrees Celsius? So I know it's going to be right in front of 30. So let's see. I would say that's probably 25. I don't think that that's where I'm looking for because that looks right in the middle. So let's keep going. Okay, so like that little guy is right in the middle. Okay, here we go. This little guy is super duper close. Okay, so we would say that NH3 and KNO3 both have the same solubility at 28 degrees Celsius. Perfect. I know we don't know what KNO3 and NH3 are. That's totally fine. I'm not asking you what they are. I'm asking you which two substances dissolve the same amount at this specific temperature. Okay, the next one says, if you have 120 grams of Ki at 10 degrees Celsius, would this be saturated, unsaturated, or supersaturated? Okay, so we're looking at 10 degrees and 120. So let's go up, 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 up. Okay, so this is where my point would be. All right, so right here. But I am looking at Ki. Ki is up here. So since I'm below the line, would that mean I'm saturated, unsaturated, or supersaturated? Unsaturated, very good, okay? So these are definitely some questions that you're gonna see as we talk about matter and changing of matter and properties of matter. So, all right guys, that's it. But yeah, have a great day. Take care.